Welcome back. In this session, we'll be discussing about another interesting sorting algorithm called quicksort. In the last session, we discussed about merge sort, which is also based on divide and conquer strategy. Now, the difference between a merge sort and a quicksort. So, the disadvantages are eliminated in quicksort. So, the disadvantages of merge sort is that it requires 2n locations. Why? Because we are using an array, auxiliary array or the temporary array B during the merging process. Also, it requires more stack space to keep track of all recursive calls. Quicksort is another sorting algorithm, an efficient sorting algorithm. Right? So here it eliminates the disadvantages with merge sort. In merge sort, the major difference between quicksort and merge sort is, in merge sort, division of the given input array into subarrays is made at its midpoint, whereas in quicksort, the division does not happen exactly at its midpoint, but the algorithm finds a pivot value or the partition element based on which the input array is divided. So quicksort is a highly efficient sorting algorithm. It requires finding the pivot element, partition element. We call it as the split point. So how do we compute how do we find the partition element? So this quicksort is based on two assumptions. All the elements are distinct. We assume the given elements, all the elements in the given array are distinct, and then the partition element, say V is equal to A of M, has the equal probability of being the ith smallest element. So we cannot say that the given element will be the smallest element. So every element has the equal probability. The partition element has the equal probability of being the ith smallest element. So based on these assumptions, let us proceed to the algorithm of quicksort. So as I said earlier, the first step is finding the partition element. So you'll understand better if we discuss an example. So look at these values. So we have, how many elements are there? Totally we have 4, 5, 6, 7, 8, 9 elements. So we have 9 elements. So we'll be maintaining two pointers, say left pointer and the right pointer. Initially we assume the first element as the partition element. First element in the array is the partition element. So in this case 54 is the first element. Now what we do is, we initialize the two pointers, that is left pointer and the right pointer. The left pointer points to the element next to the partition element, that is the first element. So it will be starting from 2. The right pointer will point to the last element, the position of the last element. Always this quicksort assumes there one element with alpha, one last position, assuming it to be infinity. So now we start comparing the elements. So we compare the element pointed by the left pointer with the partition element. So remember, we assume the first element as the partition element for now. So in this case, now the left pointer points to 26. We compare 26 with 54. So this comparison should continue until the left pointer points to a value that is greater than the partition element. So in this case 26 is less than 54. So we increment the left pointer. Now it points to 93. So 93 is compared to 54. At this place we stop incrementing the left pointer. Now we start comparing the elements from the right pointer. So the rightmost pointer points to 20. Now compare 20 with the partition element 54. Now 20 is less than 54. So we stop when the element pointed by the rightmost pointer is less than the partition element. So in this case, we interchange 26 and 93. Right? So in this case, you could see the example. Now the right pointer, so left pointer points to 93. Now we start comparing 20. Now 20 is less than 54. We stop incrementing the right pointer. So now 20 is less than 94. So interchange 20 and 93. So interchange 20 and 93. Again we continue the process with the left pointer. Now increment the left pointer, it points to 17. 17 is less than 54. So again increment the left pointer. Now the left pointer points to 77. Now in this case we stop. Why? Because 77 is greater than 54. So we stop incrementing the left pointer. Now continue with the right pointer. So right pointer already points to 93. Now we decrement the right pointer. So now it points to 55. Now 55 is greater than 54. So decrement the right pointer further. Now right pointer points to 44. So when you are comparing the elements from the right end, we have to stop only when the element pointed by the right pointer is less than the partition element. So in this case, right pointer points to 44. Now 44 is less than 54. So in this case, we exchange the elements pointed by the left pointer and the right pointer. Right? So exchange 77 and 44. So we get 44, 31 and 77. Now again continue with the left pointer. Now the left pointer will point to 31. Now compare 31 with 54. Now 31 is less than 54. So again increment the left pointer. Now left pointer points to 77. Now 77 is greater than 54. Here we stop. So left pointer, we stop incrementing the left pointer when the element is greater than the partition element. We stop decrementing the right pointer when the element pointed by the right pointer is less than the partition element. So in this case, we stop incrementing the left pointer at 77. So earlier 31 left pointer is 77. Now what is the right pointer? Now right pointer already now decrement the right pointer. Now right pointer points to 31. Now 31 is less than 54. So we stop decrementing the right pointer. So at this place you could see right pointer is pointing to 31. Left pointer is pointing to 71. Now the value, so the value of the left pointer, so in this case what is the value? 1, 2, 3, 4, 5, 6, 7. So the left pointer, value of the left pointer is 7 and the value of the right pointer is 6. So when the left pointer is greater than the right pointer, in that case we need to exchange the element pointed by the right pointer and the partition element. So in this case we exchange 54 and 31. So when the left pointer crosses the right pointer, in other words, when the left pointer is greater than the right pointer, we exchange the elements pointed by the right pointer and the pivot element, and the position of the right pointer gives you the pivot value. So that is the pivot element. Another example. So I can you could see 65 as the, you'll better understand if we discuss another example. So in this case we have totally 9 elements. So always we assume the last element to be infinity. So compare 65 is the current partition element. So 70, compare 70 with 65. It's greater, so stop. and then the right pointer is now is 45, compare 45 65, it's smaller, so we stop it decrementing the right pointer. Now interchange 45 and 70, so we have interchange. Again continue with the left pointer. Here 75 is greater than 65, so stop. Similarly decrement the right pointer. Earlier it is 9, now it is decremented to 8, so it points to 50. Now 50 is less than 65, so stop. Now interchange the elements pointed by the left pointer and the right pointer, that is 75 and 70. So, 50 and 75. So that's exchanged. Again increment the left pointer. So 55, 85. So only 85 is greater than 65. At that position we stop incrementing the left pointer. Likewise, we decrement the right pointer from 7 to 6. Now 60 is less than 65, so we stop. So in this case exchange 60 and 85. So after exchange we see now the value of just increment. Now again increment the left pointer. Now the left pointer points to 6, comes to 6. What is the value? 85. So 85 is greater than 65, so we stop. So now the value of I, here we use 2 pointers. I is the left pointer, P is the right pointer. So the value of I is 6. Now when decrement the right pointer, it goes to 5. Right? So in this case, so 60 is less than 65, so we stop decrementing the value of the right pointer. So now what are the values of left and right pointer? Left pointer points to 6. Right pointer points to 5. So left pointer is greater than the right pointer. In this case, we need to exchange the elements pointed by the right pointer and the partition element. That is, we exchange 60 and 65. So 65 comes to the 5th position and 60 goes to the 1st position. Now here, which is the pivot element? Pivot element is the 65. So here, this is the partitioning element or the partitioning position. You can call it as partitioning element or pivot element. So at this juncture, you could see all the elements that precede the pivot element are less than the pivot element. So 60, 45, 50, 55 are all less than 85. All the elements that follow the pivot element 65 are greater. So 85, 80, 75, 70. So all these 4 elements are greater than 65. That is the pivot element at position 5. So 65 is the pivot element or the pivot position. Now the input array is divided into 2 subarrays. The first subarray having 4 elements 60, 45, 50, 55. The second subarray containing 85, 80, 75, 70. So this is how the input array is divided into subarrays. So based on the pivot element. So another important difference between quicksort and merge sort is, in quicksort we don't merge after subdivision of the arrays. The elements are rearranged in such a way that finally the elements are all in their sorted position. So in merge sort we have to subdivide and finally merge. So merging process is not required in quicksort. The sorting is accomplished by just rearranging of the elements while finding the partitioning element. It's a very simple and efficient algorithm. So in quicksort, the first task is to find the partitioning element. So here we assume V is equal to A of M, that is the first element. We use 2 pointers I and J. I points to the first element and J points to the last element. So we repeat the left pointer. Here the left pointer is I, the right pointer is J. So we increment the right pointer I is equal to I plus 1 until we increment the left pointer I until the A of I is greater than or equal to V. Similarly, we decrement the right pointer j until the element is less than the partitioning element. At this stage, if I is less than j, then interchange the elements pointed by a of I and a of j. So this process continues until I is greater than or equal to j. Right? So this gives you, this partition algorithm returns the partitioning element or the position of the partitioning element. So the main algorithm for implementing quicksort is, here we assume the dimensions are the lower limit and upper limit is p and q respectively. So if p is less than q, that means the input array has more than one element. If there is only one element, there is no need to divide. So if the size of the array, if the array contains more than one element, we divide p into two subproblems. J is equal to, we find the partitioning element, the position of the partitioning element. So j represents the position of the partitioning element. Once we find the partitioning element, the input array can be divided into two subarrays. So you could solve the subproblems. Quicksort of the same algorithm is recursively called with the upper limit as p comma j minus 1, because j is the midpoint, that is the pivot, so not the midpoint, the pivot position. So the first subarray will be ranging from p to j minus 1. The second subarray will range from j plus 1 to q. So now we have two subarrays to be solved. Again, we recursively apply quicksort to sort the subarrays. So please observe that there is no need for merging in quicksort. So there is no need for combining solutions as well. So this is considered to be an efficient sorting algorithm based on divide and conquer strategy. Hope you understood the implementation of quicksort. We discussed two examples. So thank you for listening. Bye for now. Let us continue the remaining topics in the next session. Thank you.